Hey everybody, it's Mr. Sheeline here, and this is going to be the Unit 7.1 notes covering static electricity. So now we've already kind of done some examples, demos in class when it comes to static electricity, and we also did a Nearpod kind of walkthrough. So now we're going to take all that stuff that we learned in the Nearpod, a video or two that we watched during class, and we're going to kind of put it all in this nice, neat what would you call PowerPoint presentation. So here are the learning objectives that I have for you guys for this particular unit section. So I can identify and describe the nature of static electricity and electric fields. I can identify different objects as conductors or insulators, and I can describe how and why lightning strikes the earth. Ooh, a whole bunch of great stuff here. Okay, so right off the bat. So electricity. So as an example of something you may have done or some either on purpose or an accident or whatever, you walk across a rug, you reach for a doorknob and boom, zap. You get a little shock on your hand. Or maybe you're sitting in a car for a while, and when you get out of the car, you go to touch the metal door and then the metal door zaps you. Or it's like this, where you come inside from the cold, pull off your hat, and boing, all your hair stands on end. So the question is, what is going on here? What is it that's moving around, and why does it seem to happen more during the winter? And so, in order to really get a better understanding of what's happening, is that we are going to break down the pieces of just matter and try to figure out, well, what about matter? What is it in matter that's making these things do this? So remember, in the middle of every kind of atom, no matter the atom, there is the nucleus. And the nucleus contains two things. It contains the protons and the neutrons. So you have protons, those positively charged pieces, and you have neutrons that have no charge. They are neutral. And then orbiting around those atoms, you have, or I should say orbiting around the nuclei, the nucleus, you have electrons, which are negatively charged. And these things we know. We went over this earlier before in the year, and on top of that, it's something that's kind of already known coming into high school. It's something that's kind of been beaten into you, metaphorically speaking. So if you had an atom, okay, when the number of protons in an atom equals the number of electrons, the atom itself has no overall charge. It's a neutrally charged atom. So if you were to then, though, have an unbalance of these electrons, what you create is static electricity. This is the imbalance of positive and negative charges. So atoms that lose electrons have more positive charges. So this is where they have more protons. Okay. They have or atoms that lose electrons have more of a positive charge than negative charge. How did I write that? Atoms that lose electrons. Yeah, lose electrons have more positive charges than negative charges. It is a positively charged electron. An atom that gains electrons has more negative than positive particles, and this is a negative charge. So the more electrons you have than protons, what you create is an imbalance. You create static electricity. Okay. And static implies that there's a bunching. It is static. It means that it is, for the most part, not moving. Though electrons do move. Though electrons do move, especially like when you rub your socks on the floor and then you go to touch something metal, something that's metal-like or is a good conductor, which we'll get to in a bit. When you touch that thing, obviously the electrons, that buildup of energy, went from your feet up to your finger. And so they're obviously moving, but static electricity implies that there's not a constant current within a system. It implies that you have a buildup of a particular charge in a particular space, and it only then becomes a current when you then connect it to another object, which then can pass through that electricity, that energy throughout its system and throughout other systems. So static just implies a buildup. It implies, or I shouldn't say implies, but is defined as a buildup. It's defined as a non-moving, for the most part, non-moving body of electricity, of energy on a body of electrons, on a bundle of electrons. Okay, now to understand though exactly how these how it, understand how this works, we have to understand an electric field. And so an electric field is a region surrounding every electric charge in which a force of attraction or repulsion is exerted on other electric charges. It's a lot of gobbledygook to say that negative charge things are going to react in space differently than positively charged. So if we look at the picture, the image that I have here, so this example here is using a dryer sheet, and it's saying that, well, if you had a negatively charged dryer sheet, so this guy right here, if you had a negatively charged dryer sheet, this is how the electric field would interact, how basically just space interacts with this material when it's negatively charged. So here we see that a negatively charged object is going to have a force moving inwards towards it, while positively charged objects have this force kind of pushing away from it or moving away from it. So what you have here, and if you see this, I mean, you have, and this is why positive and negative charges move towards one another. So here you see this positive charge, its field or the field around it's going to kind of make it go towards this negative field, because this negative field is wanting to suck things in. This wants to push things out. So when you put two things that want to suck, or how to put that better, when you have two things that are wanting to attract more objects towards one another, next to one another, basically what you're doing is that you're creating a space that doesn't really know what to do. It's kind of pushing away from one another because they're trying to outcompete one another, and while they're trying to outcompete one another, they kind of push each other away. So anyway, the arrows show the direction of the positive charge would move when placed in the electric field. A positive charge would be repelled by a move and move away from another positive charge. Okay, a positive charge would be attracted to and move towards a negative charge. Okay. So then in class, you're going to, and actually right now, I would like for you guys to work on this. It's really nothing to work on as much as to play around with. This is a good demonstration. And what I want you to do is observe what happens when different charges are brought together using this electric field hockey PhET simulator. So you guys can either click on this link here in the Google slide version of the notes, or you can click on this image here. Both of them will take you, it'll link you to that simulation. You can go to that simulation and play around with this like little hockey thing. It's a little game to show you just how the electric field works, how the electric field interacts with all these different positive and negatively charged elements. I should say not elements, but particles. And there's it's basically a fun little game to try to play some hockey. So this one right here is arguably the hardest. This is a hard little puzzle to solve. The point is in this picture is to take this black little dot here, that's a hockey puck, to get this from here all the way over to the goal over here. That's the point of the game, to kind of snake it through here to get it into that goal. So a nice little thing to try out there. Okay, and then while you're working on that, while you're playing with that, there are some questions here. So the puck is positive. In the check your understanding, this is check your understanding number 1. So if the puck is positive, what charge do we place behind it to move it forward? What charge can be placed in front of it to move it forward? Okay, so answer those while you're playing around with that, but I'm going to keep on going. All right, so charges and objects. So I mentioned this word conductor a while ago, and hopefully it's a word that you've heard before in reference to electric fields, static electricity. Conductors are materials in which energy, specifically in the form of electrons, move most easily through. So most of these are metals. This is so if you have a parent or some sort of relative or a sibling that works in or as like an electrician, you may know that they run wire through houses or buildings in order to have a spot like an outlet where power can be drawn through. And those wires are made of metals, most likely some sort of copper composite material, because copper is a metal, and not only just a metal, but a super duper amazing efficient conductor. Energy runs through copper due to its density, due to its more or less what you could call its molecular structure. energy moves through it like it's no one's business. It just is so good at conducting energy and electricity. So, um, and that's something we know. That's why if you have an old house, or if you have an old house, you may have a lightning rod on the top of your house, or maybe you have a lightning rod somewhere near your property. And the idea is that and it's usually made of, or it's pretty much always made of metal. And the reason for that is because, again, metal is a great conductor. And what you want to do is you want to draw the lightning away from things that can catch fire and channel it in a better way, which I can get to maybe towards the end of this. But anyway, just to say that conductors are great at moving electrons through itself. So here's an example. Electrons on your shoe repel each other, and some are pushed onto your skin. Now, because your skin is an effective conductor, okay, for a number of different reasons, the electrons spread over the skin, including your hands. So that is, again, this is how when you if you're wearing socks, you rub your socks on the floor, and then you go up to someone and you touch them on the shoulder, and then you can zap them really well. It's because you are rubbing your feet against the floor. You are more or less picking up a whole lot of negative energy in the form of electrons, and those pass through you. Your skin's a great conductor. It goes from your feet all the way up to your hands. And then when you touch something, all that energy is going to go from a high concentration of energy to a low concentration of energy. It's going to diffuse through your finger, and it's going to move from high voltage to low voltage on whatever object you're touching. And in that moment, the person or thing that is receiving all of that is going to receive it in a pretty quick manner. It's going to receive it in a form of a quick shock. Now, typically, it doesn't hurt so much, though it can. It doesn't hurt the person so much who's sending it over. A lot of times it hurts the person that they're sending it to. Okay. But again, it does depend on the person, depends upon the area in which they're using, depends upon just their pain tolerance. But anyway, so that's a conductor. So electrons move easily through conductors. And then there's insulators. So these are material that do not let electrons to move in and out, and really do not really move all that easily through. So electrons are held tightly in atoms that make up insulators. So most plastics are insulators. So that's why most things like lamps, keyboards, phone chargers, anything that carries an electric charge is typically wrapped with some sort of plastic rubber material, or both, depending on its size and the amount of energy it has to move through it. So again, this is why most appliances have their cords are wrapped in plastic, because plastic does not allow electrons to move through it all that well. And that's why you can safely touch plastic, but you don't want to touch, say, like in this picture, if you were to plug this in, you don't want to touch those copper wires, because those copper wires are going to go from, again, a high voltage. Copper wires have high voltage to your hand, which is going to have a low voltage, and it's going to hurt a whole lot. In fact, it may, depending upon the appliance, it may do something more than just hurt you. It may end up killing you. So always be careful. And that's why if you have exposed wires where the plastic is not covering, you don't want to touch those things. But anyway, the plastics are great for insulating all of that energy and all those electrons. And so here's a decent list of all the things that are conductor between, what are good conductors and fair conductors versus good insulators. So now you're probably wondering, well, Mr. Sheeline, why is there not a list of bad conductors, and why is there no list of bad insulators? Well, it's because good conductors are bad insulators, and bad insulators are great conductors. And the vice versa, same thing. Good insulators are bad conductors. You don't use oil. You don't want to use fur, silk, or wool to transfer energy in the form of electricity through itself, because it really won't do it. As we know, like for instance, when we think of cars getting hit by lightning, we, for the most part, though incorrect, we think that you'll be fine because the tires are made of rubber and that will pretty much kind of stop that flow of electricity. Though there is some truth to that, it has some flaws to it, but rubber is a good insulator. It doesn't allow energy in the form of electrons to really move around all that much. Same thing for paper, wood, plastic. Okay. Whereas in good conductors, here you have your good conductors: silver, copper, gold, aluminum, magnesium, tungsten, nickel, mercury, platinum, iron. All of these things are great for conducting electricity. And here are some okay ones, some fair conductors: graphite. So that's what you put in your mechanical pencils. That's what you have in your pencils is graphite. Nichrome, the human body. Okay, damp skin. So water is a pretty good conductor. Acid solution, salt water is a better conductor than the non-salt water. The earth, water vapor in the air, silicon, and germanium. Okay, now these are just a couple of examples. This is obviously not the whole list of all kinds of different good and fair conductors. There's a whole lot more. Same thing for good and common insulators. Okay, just a short list of good examples as to what makes a good conductor versus what makes a good insulator. And remember, good insulators make bad conductors. Good conductors make bad insulators. You don't want to put copper around, say, silver, if you're having the silver carry an electric current, because the problem there is that the copper is going to move just as much, if not the same amount of energy as the silver will. And if you touch it, you're going to hurt yourself. You want something surrounding your good conductor that's a good insulator. Okay. And there's this, this stuff, ebonite right here, is basically just, it's another form of rubber, by the way. Okay. So there's a difference between conductors and insulators, and then there's something that's a separate kind of category of what's called electrostatic series. So the electrostatic series it's a way to describe how well the object will keep its how well it will keep its electrons. So a lot of these are, or as far as what's on this list over here, a good number of them, pretty much all of them, are good insulators. And there's a range of how good these insulators are. So the electrostatic series is about how well these objects can hold in electrons and not lose them. Conductors and insulators talk about how well the electrons move within that particular thing. So it's a difference between how much does something hold it inside of itself versus jumping out. Okay. So does it move quickly through the thing, or so conductor versus insulator versus this electrostatic series, which is how well does can they bounce out and jump to a different substance, or does that substance really lock in that energy? And so, again, a lot of these are insulators. So here you have strength hold on electrons. So it goes from weak, top is the weakest, bottom is the strongest. So glass, not a very good insulator. Though it is an insulator, technically speaking, because it's not a good conductor, which maybe, some teachers physicists may disagree with that. For the most part, glass just does not conduct well. But the problem is that it's a weak insulator as well. Maybe I'll say that it's a weak insulator just because it does not hold electrons well. Electrons can pass through it fairly easily. And we saw that in the example with like the jumping balls, the ones where the little balls of aluminum foil, the electrons through the PVC pipe were able to grab a hold of those aluminum balls and kind of pull them up to the glass, when really any other substance wouldn't do that for the most part. Your hair's not too great, but as far as we go down, so rubber balloon is able to hold in, those electrons fairly well. Polyester, foam, grocery bags, ebonite. Okay, there's that ebonite again, a hard form of rubber. These things at the bottom here can hold in electrons really well. So if you go down the list of items, the items have a tendency to gain electrons. Up the list, they have a tendency to lose electrons. So here, human hair loses electrons, and they lose them to balloons if you rub balloons on your hair, whereas in rubber balloon, it's going to keep those electrons. Foam will keep those electrons that it already has, or will take some electrons from something else, depending. Okay. So if you rub a human hair, and this is for check your understanding number 2 here. If you rub human hair and wool together, which will lose and which will gain electrons. So answer that one using this little chart here. Do the same thing for lucite and silk, rubber and cotton, glass and foam. All right, so then we got to talk about, well, how is it that we can have electrons jumping from one thing to another? So there's 2 basic types of ways that electrons will jump from one thing to another. There's friction or contact, and then there's induction. So friction and contact is a super duper common way that you've, again, have probably done before, consciously or unconsciously. You've rubbed your socks against the floor. You go to touch something that's a good conductor or a fair conductor, and you get zapped, and the thing also gets zapped as it transfers the electrons from you to it, or to you to them, them to whatever. You get what I'm saying. So one very common way is to rub 2 objects together. Electrons may be transferred or moved from one to the other. So the more rubbing, the more electrons move. Okay. And then there's induction. And induction is when electrons from a neutrally charged object are moved by a charged object. Now, they don't have to be moved in the sense that they are that's not moved in the sense that they are moved from one object to another. It's just that they're rearranged. So again, it's not winning or losing, because that does depend on the electrostatic series of that particular object. Does it lose them very well? Does it rearrange them all that well? What happens? So, but as an example of what an induction what induction looks like, if you've ever done this before, it's like when you take a magnet and you put it on like a nail or a screw or any like little hunk of metal that had no charge to it. It was virtually neutral. You put the magnet on it and you let the magnet kind of sit there for a while, and then you take the magnet off, and then you go up to something that will be attracted by so you take the magnet off the little chunk of metal. And then if I were to put it like here on my mic stand, let's just say for the sake of argument here, then it would probably stick to my mic stand. Even though it's not a magnet, the magnet has used induction to either rearrange or in some cases to push some energy into that object. And that object then itself kind of becomes like a magnet. Not very strong magnet, mind you, but more than it was before you toss the magnet on. So again, there's a difference between contact, friction versus induction. Okay. And so another one of induction would be if I were to take a balloon and I were to rub it on my head. Okay. What I'm doing is I'm adding negative charges to that balloon. Well, if then I took another balloon and I kind of put the other balloon next to it, okay, this balloon that wasn't rubbed will gain some of those electrons because it has it has more positive charge than this guy, and some of those negative charges will go over to this guy until it balances out, roughly speaking, and then both of them will be negatively charged. I didn't rub this one on my head or anything else to give it that charge. It basically just stole the charge from this other balloon. It did it through induction. Okay. Okay, and then I've got 3 laws to toss at you. And these are laws that again, pretty much know these already. So law 1, opposites attract. So 2 things with opposite or different charges, positive and negative, will attract and pull towards one another. Law 2, things with the same charge, 2 positives or 2 negatives, will repel or push away from one another. And so here are some good examples of where right here, opposite charges attract, but then like charges repel. And then there's a third law that positive attracts neutral objects and negative attracts neutral objects. And the idea is that these negative or neutrally charged objects just don't really have anything going for them. But when you put, say, like a balloon here, you take a negatively charged balloon and you move it closer to this object, it's not to say that you're entirely changing the chemical composition. You're not changing the chemical composition of that thing, of, say, this wall down here. What you're doing is that you're just rearranging them in this short term to make it to basically to make that object a bit more polar than it was before, meaning that you're basically making a positive end and a negative end on it, when originally it didn't really have that. So if you're to charge a balloon by rubbing it on your hair, picks up extra electrons and has a negative charge, holding it near a neutral wall will make the negative charges on the wall move away. Okay, and again, and the reason why is because this is like charges are going to push like charges away, which will then just naturally also draw those positive charges towards those negative charges. And you're probably asking, well, why don't these positive charges stick with these negative charges here? Because there's arguably more negative charges here. There's a higher concentration. And because there's a higher concentration, this wants to meet with this so it can balance it out. And that's something hopefully that you'll learn, that you're beginning to kind of pick up here, and that you'll definitely pick up when you get to like biology. And you learn more about diffusion. Diffusion is pretty much a universal, I don't want to say constant, but it's so common. The idea is that things just want, the world wants to be as balanced as possible, and it's part of an idea of systems want to use up as the least amount of energy as possible in order to complete a task. And one of those things that just tries to be as effective as possible, naturally speaking, is just kind of it's part of diffusion. It's so much easier and just to move from a place that doesn't have something to where you have a balance of one thing and another thing in two places. And so how to and now I've kind of maybe I've lost you a little bit here, but it's just, again, I guess the point is just to say that as you get older, the more you get into, say, biology, the more you'll see diffusion just is seen everywhere, whether it is biology, whether it is chemistry, whether it is physics. It's just everywhere, and everything wants to move towards places where there's not a whole lot of it. So because it's a whole lot easier to move to a place where there's not a whole lot of you to a place where there's a whole lot of you. And so an example is here. The positive charges want to move where there's a higher concentration of negative charges, because over here with these other negative charges, there's still other positive charges. Over here, there's like virtually none, and they want to move towards that to try to make this as equal as possible over here. It wants to reach that equilibrium. But the answer to that why I've already pretty much stated. It's that because like charges repel, negatives here are going to repel those guys. And the result is that there are more positive charges closer to the negative balloon and therefore attraction. Okay, one of the few last things we're going to go over, bad hair in the winter. So why is it that we have bad hair in the winter? Okay, why is our hair full of static? Why is it that when we pull clothes out of the dryer that we shock ourselves? For the most part, it's the same principle as what we've been talking. It's exactly the same principle of static electricity. It's just the fact that in the winter, though, there's less water. So what does that have to do with anything? So what does that have to do with anything? So because you have less water in the air, because there's less moisture in the air, remember, water is a good conductor. If you have less water in the air, that means that you have there's less electricity moving through that water. So that means, and that may seem like that's counterintuitive, right? That may seem like it's counterintuitive, but it's not. If you have more water in the air, electricity can just move out throughout and kind of diffuse itself throughout space a whole lot easier than if there's very little water. If there's very little water, it kind of holds itself in an object like your socks, like your sweatshirt, and it just kind of sits there and it can't move out because there's no water vapor. And so when your hand goes to touch that thing, and there's really no other water in the air, pretty much all of that energy goes right into your hand. It goes you take your hat off, all of it goes from your hair to your hat. It is water, again, is a great conductor, and the less of it that you have, the more potential you have of shocking yourself. And that's why during the winter you have bad, for the most part, it's a harder time managing your hair if you wear hats. That's why if you reach into a dryer, when you reach into a dryer after you dry your clothes, you may shock yourself because, again, there's less moisture in the air. Okay. The last thing we'll cover here is lightning. So, lightning is an interesting phenomenon, as we probably already know. So, if there are enough positive charges on one object and enough negative charges on another surface of another object, the electrons might want to jump the gap. So, and I've already been kind of talking about that as far as like when you rub your socks on the floor and you touch something, energy wants to go from high to low places because it's easier to go from high to low than high to higher or high to high. And that's pretty much what lightning's doing here. So here I've got a whole bunch of different videos on lightning. Give those a watch. All three of them, they're great videos and just showing off lightning, people being in the right place at the right time to see all these really, really cool shots. Okay. But here's what's happening. Here is what is specifically what's happening. So it's something that and I shouldn't say it's something that meteorologists are still working on as far as a very, very, very foolproof, solid explanation. But for the most part, this is the best that it can be described as. So many of the particles in a storm cloud become charged. In storm clouds, there's a whole lot of air movement. A lot of times there's a lot of different movement of warm air, cold air, and differing levels of wind, differing levels of different charges on the surface of the earth, depending upon where you're at. All these are factors into more or less what causes the stir. But convention currents in the storm, meaning just convention, meaning that they move circularly for the most part. They move within themselves. Okay, cause a charge separation. So it's just to say that they just kind of move between one another, and the bottom of the cloud becomes more negatively charged, or just a portion of the cloud becomes more negatively charged. And in this case, we'll say the bottom, and then the top. Bottom will become negatively charged. Top will become positively charged. Okay, and the negative charges on the bottom of the cloud repel the negative charges in the ground. So this would be in the ground, the tree, the house, and it basically is opening up for a target. Naturally is opening up a target to hit. So a person standing beneath the cloud might feel a tingling sensation at this point. Fair note also, apparently now you can't really test for this, and you can't, this is all testimonial, meaning that it's just it's someone who experienced this, and it's their experience, and anecdotal, it's a story, it's their opinion. There's a pretty good consensus of individuals that have been struck by lightning that you get a feeling that the hairs on the back of your neck stand up a second or two before you get hit. And now, why is that important? It's possible that if you feel that and you know exactly what's happening, if you huddle down on the ground, maybe you'll make less of a target for yourself, and that something else will get struck. But it happens so fast, apparently, that there's really nothing you can do. But anyway, fun fact, I guess. So the positive charges at the ground attract the negative charges in the cloud, remember, and those negative charges in the cloud move toward the ground once the bottom of the clouds have accumulated enough negative charges. It holds so much, there's a particular point to which it can't hold it anymore. And on top of that, there's so much in attraction that the only thing that can happen is for that negative charge to basically move through the air and then hit and find the positively charged object. So as the negative charges approach ground, positively charged ions surge upward and meet those negative charges. The result connection is a spark that you see as a lightning flash. So this is pretty much how lightning happens. It's static electricity. It's a gigantic, huge bundle of static electricity that just eventually lets itself go because it's close enough and strong enough to reach a particular positively charged item. So that's why the name of the game is during lightning strikes, don't stand under trees. Here's why. Trees can be more positively charged than things around you. Why? Because they reach higher in the sky. Don't be do not hold metal objects, especially super tall metal objects, while there's a storm. Why? Because the positive charges within that metal are going to say, hey, you're clear to land here, and while holding that metal object, you're going to get caught in the middle of that. And then if you're thinking, well, wait, Mr. Sheeline, then why can we be in houses? And if it's a house, we'll be fine. If it hits the house, relatively speaking, you'll be fine. Like, you won't be electrocuted if you're, say, not in the shower, or generally speaking. If you're not in the shower, you'll be fine because there's so many other insulators throughout the house that it diffuses and locks in the electricity coming from the lightning and won't hit you. Though your house may catch on fire, that's still very much not or a possibility too. So anyway, so that's pretty much the end of the lecture here, guys. If you have any questions for me, make sure you let me know. If not, I'll see you in the next one.